Hello there, and welcome to the Sleepy Space Channel. Tonight, we are drifting through the quiet neighborhood we have always called home, our solar system, with its single warm star and its 8 slow, patient companions moving through the dark. There are icy mountains on a world at the edge of the sun's reach, and blue-tinted sunsets on a cold red planet, and a moon of Saturn where rain falls as liquid methane into still, dark seas. There are geysers rising from beneath the ice of a small, frozen world, and a cloud of ancient travelers drifting so far from the sun that they barely remember it is there. Tonight, none of it is far away. Tonight, all of it is simply home. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Allow the day to quietly step back, and let the dark above you become something wide and familiar and still. Let's begin. There is a sky above you right now, and it is already in motion. You do not need to do anything about that. You do not need to understand it quickly, or hold it all at once, or trace the paths of every object moving through it. Everything up there has been moving since long before you arrived, and it will continue moving long after this particular night has passed. The solar system is not a distant thing. It is not a subject in a textbook, or a diagram on a wall somewhere, or a collection of facts that needs to be sorted and filed before you can rest. It is simply the neighborhood. It is the arrangement of matter and light and slow orbital motion that you have always been living inside of, without necessarily thinking about it, which is exactly how a neighborhood should feel. The sky that is above you right now is not empty. That is the first thing, and perhaps the most quietly comforting one. Space, in the popular imagination, is often described as a void, a nothing, a black absence between points of light. But the space inside our solar system is threaded with things. There is a continuous breath of charged particles, moving outward from the sun in all directions, every moment, reaching past every planet and moon, and drifting fragment of rock all the way to the very edge of the system. There is light traveling outward on those same invisible pathways. There is gravity, which does not move at all, but simply is a continuous shaping of the space between things, organizing every object in the system into its own particular curve of motion. None of this requires your awareness to operate. It has never required anyone's awareness to operate. The sun sits near the center of all this motion, not quite at the mathematical center of the system's mass, but close enough that from anywhere inside the solar system, it reads as the organizing principle, the thing everything else is slowly turning around. You can picture it as something like the center of a very quiet room. Not a room with walls, not a room with furniture exactly, but a room with a warm center and a darkness that gradually deepens as you move outward, and small objects scattered at various distances, each one tracing its own loop around that central warmth. That is the solar system. That is what you are resting inside of tonight. It is a strange comfort, perhaps, to think of the solar system as a neighborhood rather than a system. A system implies mechanics, precision, inputs and outputs. A neighborhood implies something softer, a place where things have been for a long time, where the rhythms are familiar even when unnoticed, where the presence of other objects nearby gives a kind of structure to space without demanding anything of you. The moon has been in its orbit for billions of years. Jupiter has been tracing its slow circle around the sun for so long that the number of times it has completed that circle exceeds the imagination. And tonight, While you are resting here, all of that is continuing, quietly, without effort, in the dark above you. The sun, when you think of it gently, is just another star. That is a phrase that sounds almost dismissive, but it is meant as a kind of warmth. There are hundreds of billions of stars in the galaxy, and most of them are roughly similar to ours, small to medium in size, burning steadily, surrounded by a region of space where their gravity and their light shape everything nearby. Our sun is not exceptional among these. It is not the brightest star in the galaxy, not the largest, not the most active. It is, by most measures, a fairly ordinary middle-aged star. And yet, because it is so close, it is the entire sky for us. It is the thing that marks morning and evening, that makes seasons, that drives weather and climate and the rhythms of biological life on the third planet out. Its proximity is everything. Its ordinariness is what makes it so quietly perfect for the neighborhood it has built around itself. To think about orbital motion as a kind of breathing can be useful when you are settling into stillness. Breathing is continuous, rhythmic, reliable. It does not require thought. It does not pause for observation. A planet in orbit moves along its path in the same way, not because anything is pushing it, but because the curve of space around a massive object creates a path that a moving object simply follows. The planet is not trying to orbit. It is simply moving, and the shape of space around the sun means that moving naturally becomes a curve, and a curve that brings you back around to where you started becomes a loop, and a loop repeated enough times across enough centuries becomes simply the way things are. Earth moves around the sun in 365 days and a few hours. It has done this approximately 4.5 billion times. There is nothing urgent about that number. It is simply how long the neighborhood has existed. You might notice, if you let your attention rest on the image of the night sky without trying to pass it, that there is a quality of structure to it, even when you do not know the names of things. Some lights are steady, some faintly shift over the course of weeks. Some trace a narrow band across the sky that corresponds, though you may not think about it this way, to the flat disk of the solar system seen edge-on from inside it. The planets move along that band because the solar system is shaped like a disk, a thin, flat arrangement of orbiting material, all of which formed from the same rotating cloud of gas and dust billions of years ago. The rotation of that original cloud is what gave everything its direction of motion. It is why the planets all orbit in the same direction. It is why the sun itself rotates in that same direction. Everything in the system remembers, in the language of physics, the original spin of the cloud that made it. The scale of the solar system is one of those facts that resists easy visualization, and perhaps that is all right. You do not need to hold it all at once. What might be worth holding, gently, as you begin to settle into this quiet audio space, is simply the idea that distance here is not frightening. It is comfortable. The distances between objects in the solar system are large enough that each planet occupies its own territory, its own region of space, without crowding or competing. The distance from the Sun to the Earth is approximately 150 million kilometers, which sounds large and is large, but it is also the distance that sunlight travels in about 8 minutes, which means that every time you feel sunlight on your face, you are receiving light that left the sun 8 minutes ago. There is something gently time-displaced about that. Something that reminds you that even something as ordinary as daylight carries a small delay, a soft lag between source and arrival, as if the universe were being just slightly unhurried about delivering the message. The solar system does not end at Neptune, though Neptune is the farthest of the 8 major planets. Beyond Neptune, there is the Kuiper belt, a wide region of icy small bodies. Beyond that, a more scattered zone of distant objects in elongated orbits. And beyond that, theorized but not directly observed in full, a vast spherical cloud of icy material that surrounds the entire system in every direction, not just the flat disk plane, but above and below, and to every side, a sphere of quiet frozen things drifting at enormous distances from the sun, barely held by its gravity, occasionally nudged inward by the gravitational presence of passing stars or the slow tidal pull of the galaxy itself. The solar system, in that sense, is much larger than the planets. The planets are just the busy part near the center. This is the neighborhood you are resting inside of tonight. It is larger than it appears, quieter than you might expect, and in motion in ways that do not require your participation. As your breathing slows and your thoughts begin to soften, you can let the image of the night sky settle above you, not as something to study, not as something to solve, but as something that has been there all along, patient and continuous, the very oldest version of a familiar view. The sky is no longer just above you now. It is structured. It has a center, a warm, quiet one, and it draws the eye outward along a series of slow curves toward worlds that are stranger and quieter and more varied than you might have thought. We begin there with that center, that ordinary star, that gentle source of everything in the neighborhood. The sun has been burning for approximately 4.5 billion years, and it will continue burning for approximately another 5 billion years after tonight. Those are numbers that resist feeling, and that is fine. What matters, for the purposes of this quiet hour, is that the sun is not new, and it is not ending. It is in the long, stable middle of its life, doing what it has always done, converting hydrogen into helium in its core through a process of nuclear fusion that generates an enormous and continuous release of energy. This has been happening every moment, without interruption, since before the Earth existed. It will continue happening every moment for a time so long that the mind cannot meaningfully inhabit it. The sun is, in the most literal sense, the most reliable presence in this neighborhood. It is easy, from Earth, to imagine the sun as something like a fire, a large, very hot fire burning in space. But fire is a surface process. It consumes fuel from the outside and produces light and heat as byproducts. The sun works from the inside. At its core, the pressure is so high and the temperature so extreme that hydrogen atoms are forced close enough together that they fuse. They become helium. And in that transformation, a small amount of mass is converted directly into energy. This is the energy that eventually becomes sunlight. This is the energy that warms the surface of every planet in the system, that drives weather on Earth, that feeds every photosynthesizing organism that has ever existed. All of it from that quiet, continuous transformation happening 69 million kilometers below the sun's surface, which itself is already 93 million miles from where you are resting. What is interesting, in a soft and meditative way, is how long it takes for that energy to escape the sunday. Light, once created in the core, does not simply travel outward in a straight line. The interior of the sun is so dense that a photon, a particle of light, immediately collides with another particle and is absorbed and re-emitted, then collides again, absorbed and re-emitted again, zigzagging slowly outward through an enormous sphere of extremely compressed plasma. This process of gradual, interrupted outward migration takes a very long time. Estimates suggest that a photon of light generated in the solar core might take thousands of years, possibly much longer, depending on which path it happens to take to finally reach the surface. And then, once it reaches the surface, it crosses the remaining 93 million miles to Earth in approximately 8 minutes. The long journey through the interior, and then the brief sprint to us. There is something quietly moving about that. The light arriving through your window today left the core of the sun during a period of human history that may not have yet included writing. The surface of the sun, called the photosphere, is not a solid surface in the way that a planet's surface is. It is a layer, the outermost layer, that is dense enough to be opaque to visible light, which is why when you look at a photograph of the sun, you see a defined disk rather than a gradual fade. Below the photosphere, the sun is too dense for light to escape directly. Above it, the gas thins quickly into the atmosphere. The photosphere itself is in constant slow motion. It has a texture, visible in close photographs, that resembles a very slow, very large-scale version of boiling liquid. Not chaotic, but rhythmic, with cells of hotter material rising from below, spreading across the surface, cooling slightly, and sinking back down. Each of these cells is roughly the size of a small country. They rise and sink in a cycle that takes several minutes. And there are millions of them, covering the entire surface, all moving at once in this enormous quiet pattern that is simply the top of a sphere of plasma maintaining its own gentle internal circulation. Sunspots are cooler regions on the photosphere, not cold in any ordinary sense, but cooler than the surrounding surface, which makes them appear darker in contrast. They are shaped by the sun's magnetic field, which is complicated and changeable in ways that the Earth's magnetic field is not. The sun rotates, but it does not rotate as a rigid body. The equatorial regions rotate faster than the polar regions, which means the magnetic field lines that thread through the sun become gradually twisted and tangled over time. When magnetic field lines bunch together and push through the surface in concentrated regions, they inhibit the circulation of hot material from below, creating those cooler, darker patches. These patches tend to appear and disappear over a cycle of approximately 11 years. Sometimes there are many of them, sometimes very few. This cycle has been observed and recorded for centuries. It is one of the most reliable rhythms in the solar system, slow and predictable as the turning of seasons. The sun has an atmosphere above its photosphere, a thin, hot, diffuse region that extends far outward and in some ways never fully ends. The innermost layer, just above the visible surface, glows with a pale pinkish light and is visible briefly during total solar eclipses, when the moon covers the bright disk precisely enough to let the dimmer surrounding glow show. Above that is a region that does something initially puzzling. It is far hotter than the surface below it. This is not what you would expect. You would expect temperature to decrease as you move away from the energy source. And yet the outer atmosphere of the sun reaches temperatures many times higher than the surface through a mechanism that involves the magnetic field releasing energy into the surrounding gas in ways that are still being studied and refined in understanding. It is one of those open questions in solar science, not a mystery that keeps you awake, but the comfortable kind. The kind that simply means there is still more to understand, like noticing that a familiar path has a turning you have not taken yet. The solar wind is the name given to the continuous stream of charged particles, mostly protons and electrons, that the sun releases in all directions, constantly, at all times. It is not a wind in the way that Earth's wind is a wind. It is not driven by pressure differences in an atmosphere. It is a flow of particles accelerating outward from the sun's corona and escaping the sun's gravity to travel through the entire solar system. This wind reaches Earth, reaches Jupiter and Saturn and Neptune, keeps going past Pluto and past the Kuiper belt, and eventually, at an enormous distance from the Sun, begins to slow and press against the interstellar medium, the very thin gas and dust that fills the space between stars. The region carved out by this solar wind is called the heliosphere. It is a bubble. Not a sphere exactly, because the Sun is moving through the galaxy and the solar wind is pressed back on one side and extended on the other, but conceptually a bubble, a region of space dominated by the Sun's output, inside of which everything in the solar system exists. Where the solar wind slows to a stop and interstellar material begins to push back, you reach the edge of this bubble. Spacecraft have crossed into that region, registering the change in particle populations and magnetic field direction. It is not a sharp boundary. It is more like a gradual transition zone, a region where the Sun's influence fades and the background of the galaxy begins to be felt more directly. Crossing it does not feel like crossing a wall. It feels, if you imagine it softly, like walking from a lit room toward a window at night, the interior light slowly giving way to the ambient dark outside, no precise line where one becomes the other. The Sun's light reaches every planet differently. Mercury receives it at intense concentration, close and unshielded. Venus receives it through thick clouds that scatter and trap it. Earth receives it at the moderate distance that allows liquid water and seasons. Mars receives it slightly diluted, softer, and cooler. And by the time sunlight reaches the outer planets, it has spread across such a large sphere of space that it is a fraction of its original brightness, enough to keep the planets from total darkness, but dim enough that midday on Neptune would look more like a dim grey overcast Earth morning than a sunny day. The Sun is still visible from all of these distances as a bright star, by far the brightest object in the sky, but it would no longer feel warm in any direct way. The Sun will not always be this way. In approximately 5 billion years, it will have exhausted the hydrogen in its core and will begin to change, expanding gradually into a cooler, larger form, brightening significantly over a very long transition period, before eventually settling into a dim, dense remnant. That transition lies so far in the future that it has no meaningful connection to anything happening now. It is mentioned not for urgency, but for the opposite, because 5 billion years of steady, reliable output stretches ahead of tonight in a way that should feel like rest. There is no rush here. There is no approaching change that concerns this quiet evening. The sun that rose this morning will rise again tomorrow, and the day after, and for billions of days after that. Its light arrives at the same 8-minute delay it always has, carrying in it the quiet record of a core that has been faithfully at work since long before this neighborhood had any planets at all. Moving outward from the sun, the first 4 worlds you encounter are all made of rock. They are dense, solid-surfaced, relatively small compared to the giants farther out, and all formed from the same swirling disk of material that eventually organized itself into a system. But despite their shared origins, they became 4 completely different places, 4 different answers to the question of what happens when a rocky world sits at a particular distance from a star. The differences between them are not small. They are enormous and complete. And yet, when you think of them together as a group, there is something quietly beautiful about the variation itself. 4 siblings, same materials, same starting conditions, shaped by distance and chance into 4 entirely different outcomes. Mercury is the innermost planet and the smallest of the 4 rocky worlds. It is a world dominated by iron. Its core is proportionally much larger than those of the other rocky planets, taking up a significant fraction of its total volume. The surface of Mercury is heavily marked by ancient impact craters, preserved for billions of years because the planet has almost no atmosphere to speak of, no wind, no weather, no erosion. And so features that formed in the distant past simply remain there, recorded in the surface like a diary that was never updated. The planet's surface looks, in photographs, somewhat like the moon gray, heavily cratered, old. But under that surface is one of the more quietly interesting things in the inner solar system, a partially liquid iron core, still active despite the planet's small size, generating a weak but detectable magnetic field. Mercury's rotation is slow. It rotates 3 times for every 2 orbits it completes around the Sun, a ratio that was established long ago by the gravitational tug of the Sun on the planet's slightly uneven shape, locking it into a stable but unusual rhythm. This means that a solar day on Mercury, the time from one sunrise to the next, is actually twice as long as a Mercurian year. The Sun rises, climbs to the top of the sky over months, and then sets after the planet has already completed one full orbit and begun another. On the surface, temperatures swing between extremes, extremely hot where the Sun beats directly, extremely cold on the dark side because without an atmosphere to redistribute heat, each face of the planet simply holds whatever temperature the Sun decides to give it, or takes away, with no moderation. And yet, despite this stark contrast, Mercury has ice. It seems counterintuitive, the closest planet to the Sun, and it has water ice. But certain craters near the poles of Mercury never receive direct sunlight. Their interiors are permanently shadowed, and in that permanent shadow, temperatures never rise high enough to sublimate ice that may have arrived there over billions of years through cometary impacts. The ice sits quietly in those craters, untouched by the extremes just outside their rim, preserved in the coldest pockets on the hottest planet. Venus is the second world from the Sun, and in terms of size, it is the most similar to Earth of all the planets. Nearly the same diameter, nearly the same density, formed from similar materials at a similar time. And yet Venus and Earth are about as different as 2 planets could be. The surface of Venus is hidden beneath an unbroken, globe-spanning layer of thick cloud that reflects sunlight so efficiently that Venus is the brightest natural object in the night sky after the Moon. Those clouds are not made of water vapor. They are made of sulfuric acid droplets, suspended in an atmosphere that is mostly carbon dioxide, layered dozens of kilometers deep. Below those clouds, the atmosphere is so thick that the surface pressure is approximately 90 times that of Earth's surface, comparable to the pressure you would feel about 900 meters below the surface of an ocean. The surface temperature on Venus is extremely high, higher than Mercury's dayside temperature, despite Venus being farther from the Sunday. This is because Venus has undergone what is often called a runaway greenhouse effect. Carbon dioxide traps heat efficiently, and with so much of it in the atmosphere and no mechanism to remove it, the heat the planet absorbs simply cannot escape. The surface bakes continuously, at temperatures high enough to melt lead. And this has been the case for a very long time. Whether Venus was once different, whether it had oceans, whether the surface once looked more like Earth's, is something that planetary scientists think about carefully. The planet may have resurfaced itself geologically at some point in the relatively recent past, relative to the age of the solar system, meaning that older evidence is buried or gone. One of the quieter peculiarities of Venus is the direction of its rotation. Almost every planet in the solar system rotates in the same direction counterclockwise when viewed from above the solar system's north pole. Venus rotates in the opposite direction, very slowly, so slowly that its day is longer than its year. A Venusian day 1 rotation takes approximately 243 Earth days. A Venusian year-one orbit around the Sun takes approximately 225 Earth days, which means that on Venus, the year ends before the day does. The Sun, if it could be seen through the clouds, would rise in the west and set in the east, and it would do so only rarely, each sunrise separated from the last by more time than any human season. Earth, when introduced in this way as the third of four rocky worlds, in the context of its siblings takes on a different quality. It is not exceptional by the standards of rocky planets. It is one of four, formed from the same disk, made of mostly the same materials. What makes it what it is, from this detached, astronomical perspective, is a combination of distance, mass, and early chance. A distance from the Sun that allows liquid water to exist stably on the surface, a mass large enough to hold a significant atmosphere, and an early history that, by some combination of factors still studied and debated, led to the accumulation of liquid oceans and the development of a chemistry that eventually became biology. From within the solar system, Earth is the water world, the only planet where liquid water currently exists in large quantities on the surface, covering roughly 70% of it in a single continuous ocean system that the planet's continents divide into named regions. Mars is the fourth rocky world and sits at what might be thought of as the outer edge of the zone, where liquid water could have been present for extended periods in the past. Mars today is cold and thin. Its atmosphere is about 1% as thick as Earth's, mostly carbon dioxide, providing almost no insulation and almost no weather in any meaningful sense. Dust devils cross its surface. Seasonal changes in the polar ice caps occur as carbon dioxide freezes and sublimes with the changing seasons. But the planet's surface is marked everywhere by features that seem to record a different past valley networks that look like they were carved by flowing water, ancient lake beds where minerals formed in the presence of liquid, shoreline features that might correspond to an early shallow sea in the northern lowlands. If Mars once had standing water, it was a very long time ago. The water that remains is locked in polar ice caps and in subsurface reservoirs as ice mixed into the soil. The surface today is dry and quiet. The color of Mars, its characteristic reddish-brown appearance, comes from iron oxide rust in the dust that covers much of the surface. That dust is extremely fine, capable of being lifted by the thin winds and spread across the entire planet in global dust storms that can last for months and dim the sunlight reaching the surface. The sky of Mars, during a clear period, is not blue as Earth's sky is blue. It is a pale butterscotch color during the day, owing to the fine dust always suspended in the thin atmosphere. At sunrise and sunset, the colors reverse in an interesting way. Mars has a blue glow near the Sun at those times, a soft, quiet blue that appears briefly before fading into the dust-tinted atmosphere. It is a small, quiet beauty on an otherwise stark world, a planet that is cold and dry and thin-aired, but not without its own soft moments. Of all the objects in the solar system, none is more familiar and perhaps less examined than the one you are resting on right now. Earth is a rocky world, the largest of the four inner planets, covered mostly in liquid water and wrapped in a thin, atmospheric layer that is just thick enough to make the surface habitable and just transparent enough to let light through in both directions. From space and from the surface of the moon, Earth appears as a blue and white sphere, the blue from its oceans, the white from its cloud systems, the occasional tan or green of land. It is, as seen from the outside, unmistakably a water world. The oceans of Earth cover approximately 361 million square kilometers of surface area. They are on average about 3.5 kilometers deep. They contain something like 1.3 billion cubic kilometers of water. This water cycles continuously evaporating from the surface, rising into the atmosphere, condensing into clouds, falling as precipitation, flowing back into the oceans through rivers and groundwater. The cycle operates on timescales ranging from days to centuries, and it shapes everything about the experience of being on Earth: the weather, the climate, the distribution of ecosystems, the softening of temperature extremes that would otherwise make many parts of the surface uninhabitable. The oceans are vast, slow, and patient, and they cover most of the world. Cloud systems, viewed from above, are among the most beautiful features of the planet. They organize themselves into patterns, spiraling low-pressure systems in the mid-latitudes, bands of continuous cloud in the tropics, long curving streaks of high-altitude cirrus following the jet stream. From a satellite, you can watch those systems move across the planet in slow, elegant loops, reshaping the planetary face over the course of days. The atmosphere is about 100 kilometers thick in total, though most of it is concentrated in the lowest 10 to 15 kilometers. Above that, it thins quickly into something approaching the vacuum of space. That thin layer is what gives Earth its blue sky, its red sunsets, its protection from the kinds of radiation that would otherwise make the surface inhospitable. The magnetic field of Earth is generated by the slow churning of molten iron in the outer core, a process called a geodynamo, which converts the heat-driven motion of conducting fluid into electrical currents, and from those currents, a magnetic field. The field extends far into space around the planet, forming a region called the magnetosphere that deflects most of the charged particles in the solar wind around the planet, rather than allowing them to strike the surface. This deflection is responsible, among other things, for the aurora's glowing curtains of light that appear in the upper atmosphere near the polar regions, when some portion of the solar wind particles do penetrate along the magnetic field lines and collide with atmospheric gases. The auroras are quiet, moving, continuously changing. They are the visual trace of an interaction that has been happening for as long as Earth has had its magnetic field and the Sun has been producing its wind. The Moon is Earth's only natural satellite, and it is a large one relative to the size of the planet, large enough that the Earth-Moon system is sometimes considered a double planet rather than a planet with a moon. The most widely accepted model of the Moon's origin involves an early collision between the forming Earth and a Mars-sized body in the very early solar system, a grazing impact that threw enormous quantities of material into orbit, material which gradually coalesced into the Moon over a relatively short geological time period. If this model is correct, then the Moon carries in its composition material that was once part of Earth, and Earth was shaped in part by the subtraction of that material. They are, in that sense, partially the same body. The Moon orbits Earth at an average distance of approximately 384,000 kilometers. It completes one orbit every 27 days or so, and because of tidal locking, a process by which the gravitational interaction between two bodies slows a Moon's rotation until its rotation period matches its orbital period, the Moon always presents the same face toward Earth. The far side of the Moon, which Earth's surface never sees directly, was first photographed by spacecraft in the 1950s and revealed to be somewhat different from the near side, more heavily cratered, with fewer of the dark basaltic plains that make the near side's familiar face. The Moon rotates just once per orbit. It is not frozen still, it simply rotates in perfect synchrony with its path around Earth. The Moon's gravitational pull on Earth creates the tides. This is a gentle but continuous force, The slight difference in the Moon's pull between the near side and far side of Earth creates a tidal bulge in the oceans, a slight elongation of the water envelope that follows the Moon as it orbits. This tidal force also acts on the solid Earth, which flexes slightly, not visibly to any person, but measurably. The tides in the oceans are the most familiar expression of this interaction, the steady rise and fall of coastal water levels that has set the rhythm of coastal life throughout human history. That rhythm comes directly from the Moon's position in its orbit. The Moon is also slowly moving away from Earth. The tidal interaction that creates those ocean bulges is not perfectly aligned with the Moon's direction. Earth's rotation carries the bulge slightly ahead of the Moon's orbital position, and the gravitational attraction between that bulge and the Moon transfers a small amount of energy from Earth's rotation to the Moon's orbit. Over long periods of time, this causes the Moon to drift slowly outward and Earth's rotation to slow very slightly. The Moon is currently receding at approximately 3 to 4 centimeters per year, about the rate at which fingernails grow. Over the lifetime of the solar system, this has added up significantly. The Moon was much closer in the very early Earth, which would have made the tides dramatically higher and the days much shorter. There is a particular quality to the Moon's appearance in the night sky that is hard to attribute to any single feature. It is the right apparent size, not too large, not too small. It is bright enough to cast shadows, but not bright enough to wash out the stars. It moves through its phases in a cycle that feels familiar even when untracked. It has been the brightest regular feature of the night sky throughout the entire history of human experience, and it continues to be that tonight, the same Moon, the same orbit, the same patient companion to a world it has been circling for billions of years. Mars has a canyon. This is a sentence that does not quite prepare you for what the canyon actually is. The canyon system on Mars, called Valles Marineris, stretches approximately 4,000 kilometers along the planet's equatorial region, about the length of the continental United States, from coast to coast. At its widest, it is approximately 600 kilometers across. At its deepest, it reaches approximately 7 kilometers below the surrounding plateau. The Grand Canyon on Earth, which feels so enormous to anyone who has stood on its rim, would fit inside one of the smaller tributary systems of Valles Marineris without difficulty. The canyon was not carved by flowing water in the way that Earth's canyons are carved. It formed primarily through tectonic stretching and rifting of the Martian crust, combined with collapse and erosion, over an enormous period of time. And because Mars has no active weathering in the way that Earth does, no rain, no rivers, minimal wind erosion, much of the detail of those ancient walls is still preserved. Near the canyon system, but to the northwest, Mars has a volcanic region of extraordinary scale. The volcano Olympus Mons rises approximately 22 kilometers above the surrounding plains, roughly 2.5 times the height of Mount Everest above sea level. Its base is approximately 600 kilometers across. It is so large that if you stood at its center, you would not be able to see its edges. They would be below the horizon. It is the largest known volcano in the solar system. And yet it does not look, from photographs, like a steep, dramatic peak. It is a shield volcano, a broad, gently sloping dome of accumulated lava flows, more like a vast, elevated plain than a sharp mountain. Its slopes rise so gradually that you would feel you were walking on flat ground for much of the ascent. The surface of Mars is quiet now. The volcanoes are dormant, or very nearly so. There may be residual internal heat, and there may be occasional small geological activity, but the era of massive volcanic outpouring that built up those enormous structures ended long ago. What the surface does now is move dust. Wind, even in the thin Martian atmosphere, is capable of mobilizing the fine iron oxide dust that covers much of the surface, lifting it into the atmosphere and carrying it over long distances. Regional dust storms are common. Global dust storms, events that cover the entire planet, happen occasionally, typically during the Martian spring and summer in the southern hemisphere, when the planet is closest to the Sun and the temperature gradient drives stronger circulation. During a global dust storm, the Sun dims to a dull glow, and the sky turns a deeper, more opaque ochre. Then, over weeks or months, the dust settles back out, and the sky gradually clears again. The polar ice caps of Mars are layered. They are not simply accumulations of frozen material sitting on top of a uniform surface. They are built up in annual layers each Martian year. Carbon dioxide in the atmosphere freezes out onto the polar cap during winter and sublimes back into gas during summer. And in this cycle, thin layers of ice are separated by thin layers of dust. The caps are like slow geological records of Martian climate history. The layers readable, the way tree rings are readable, a record of seasons and years, stacked carefully over thousands of Martian years. At the center of the northern cap, beneath the seasonal layer, is water ice, permanent, ancient, compressed into a dome that has been there for an enormous span of time. The two moons of Mars are small and irregular in shape, more like captured asteroids than like the moon around Earth. Phobos and Deimos orbit so close to Mars that Phobos, the inner one, rises in the west and sets in the east, racing around Mars so quickly that it completes more than 2 orbits in a single Martian day. Phobos is also slowly spiraling inward toward Mars. In approximately 30 to 50 million years, it will either collide with the planet or more likely be torn apart by tidal forces before it gets close enough, scattering its material into a ring around Mars. For now, it orbits quietly and quickly, a small, battered, oblong object, circling at a distance of fewer than 6,000 kilometers from the surface. Deimos is smaller, farther, and quieter, so far from Mars, relatively, that it takes 2.5 days to complete each orbit. From the Martian surface, Deimos would appear as a small, bright point in the sky, slightly larger than a bright star, but far smaller than the moon appears from Earth. It would be visible during the day if the sky were clear enough. Phobos would be more noticeable, not circular like the moon, but clearly a disk shape, moving visibly across the sky even as you watched it, rising in the wrong direction relative to the stars. The sky of Mars at sunset turns blue near the sunday. This is almost the mirror image of Earth's sky, which is blue everywhere during the day and red near the horizon at sunset. On Mars, the daytime sky is a dusty butterscotch, and at sunset, the sky near the Sun briefly shows a blue glow, the result of fine dust scattering blue light preferentially when the Sun is at a low angle. These blue Martian sunsets were photographed by spacecraft on the surface, and the images have a quiet, particular beauty, an alien world producing something that, in color at least, echoes a familiar terrestrial moment, but in reverse. Mars is, in many ways, a transitional world, the last of the rocky inner planets, sitting at the edge of the zone where the solar system changes character. Beyond Mars, the pattern shifts. The next major collection of matter you encounter is not a planet, but a scattered distribution of remnant material, spread across an enormous region of space, moving in countless individual orbits, never quite managing to organize itself into a single world. Mars is the boundary. The quiet, red, dust-settled boundary between the inner rocky solar system and the emptier, stranger space beyond. Between the orbits of Mars and Jupiter, There is a region of space that was once thought to hold a missing planet, a world that should have formed but did not. The reality is somewhat different and, in its way, more interesting. The asteroid belt is not the remains of a destroyed planet. It is the remains of material that never successfully became one. The gravitational influence of Jupiter, so massive and so close, prevented the small bodies in that region from accumulating into a single, larger body. Every time they began to gather, Jupiter's gravity stirred the pot, raising orbital velocities, changing inclinations, making collisions between bodies more disruptive than constructive. And so the material that sits in the belt today is, in a sense, original solar system material, unchanged since the early days of the system's formation, preserved in the cold and quiet of space. The total mass of the asteroid belt is small, much smaller than you might expect if you imagined it as the debris of a destroyed planet. All of the belt's material combined would make an object smaller than the Moon, and most of that mass is concentrated in a few of the largest bodies. Ceres is the largest object in the asteroid belt, and, by the definition used since the early 2000s, a dwarf planet spherical, massive enough that gravity has shaped it into a round form, but not massive enough to have cleared its orbital neighborhood of other debris. Ceres has a diameter of approximately 945 kilometers. It accounts for roughly 1/3 of the total mass of the entire belt by itself. And in some respects, it does not look like what you might picture when you think of an asteroid. It is round. It appears to have had geological activity at some point in its past, and beneath its surface there is evidence of water, ice, and possibly a layer of briny liquid water or mud. Bright spots on the surface of Ceres attracted attention when they were first clearly photographed up close. These bright features sit in impact craters and appear to be deposits of salt material left behind as water-bearing substances sublimed or evaporated, concentrating the dissolved minerals into reflective patches. They are the faint trace of a process that happened long ago, the bright remnants of ancient internal activity preserved in a small, cold, airless world. Vesta is the second largest body in the asteroid belt, not a dwarf planet, but among the brightest objects in the sky when it passes at its closest to Earth. Vesta is irregular in shape, but has a clear geological history. It differentiated early in its history, meaning that when it was heated by radioactive decay and possibly by impacts, it separated into a metal-rich core and a rocky mantle and crust, much as the terrestrial planets did. Vesta experienced a massive impact near its south pole that carved out a crater so large that material from it was ejected throughout the inner solar system. Some of that material eventually arrived on Earth as meteorites, actual pieces of Vesta that have been sitting in museum collections and on laboratory benches, identifiable by their composition. The belt contains hundreds of thousands of objects, large enough to be catalogued, and millions more smaller ones. They are not distributed randomly. Jupiter's gravity creates gaps in the belt regions where the orbital period would be a simple fraction of Jupiter's orbital period, creating a resonance that repeatedly kicks objects out of those orbits over long timescales. These gaps, called Kirkwood gaps after the person who identified them, divide the belt into different zones. Objects near the inner edge of the belt tend to have a different composition from those near the outer edge, drier and more rocky near Mars, darker and more carbon-rich and volatile-bearing near Jupiter. Jupiter also has populations of asteroids that share its orbit, sitting in gravitational stable points 60 degrees ahead of and 60 degrees behind the planet in its path around the Sunday. These are the Trojan asteroids. Jupiter has enormous numbers of them, more than 1 million objects larger than a kilometer. The Trojans have been in those orbital positions since the early solar system, and they are thought to preserve material from a wide range of distances from the Sun, swept into those positions during the period when the giant planets were migrating to their current locations. They are a preserved sample of early solar system chemistry, and they continue orbiting quietly in their two groups, one leading Jupiter and one trailing, like slow and patient companions that have never fallen away. Traveling through the asteroid belt in the imagination, it feels like it should feel dense and dangerous. Science fiction has populated it with tight navigational hazards, rocks everywhere, barely room to pass. The reality is much emptier. The average distance between objects in the belt is enormous, typically hundreds of thousands of kilometers between any two bodies of significant size. A spacecraft traveling through the belt is extremely unlikely to come close to anything at all. The belt is vast and sparsely occupied, a place of enormous distances and quiet drifting objects, not a crowded obstacle course. The material is there, but spread across such a large volume of space that the emptiness between objects is the dominant quality of the experience. Jupiter is the largest planet in the solar system by a substantial margin. It contains more than twice the mass of all the other planets combined, more than all of them added together and then doubled. If you were to gather every planet, every moon, every asteroid and comet and distant icy object in the solar system into a single pile, and then compare that pile to Jupiter alone, Jupiter would still outweigh it significantly. It is not the largest thing in the solar system the Sun contains, nearly all of the system's mass, and Jupiter is a small fraction of that. But among the planets, Jupiter's dominance is so complete that the others feel almost like afterthoughts by comparison, small, rocky, or icy things scattered around the edges of the system, while the giant at the center of the outer planets simply continues to be enormous. There is a way of describing Jupiter that gives a sense of just how close it came to being something else entirely. If you removed the Sun from the solar system and replaced it with Jupiter, the resulting object would almost be a star. Not quite Jupiter is approximately 80 times too small in mass to ignite the hydrogen fusion that defines a true star. But it would be what astronomers call a brown dwarf, an object that gathered enough mass to begin compressing its interior and generating some heat, but not quite enough to cross the threshold into sustained nuclear burning. Jupiter sits at the boundary between planet and failed star, not because of any particular drama in its history, but simply because of how much mass happened to gather there during the early solar system. It is large, dense with hydrogen and helium, and it radiates more heat outward into space than it receives from the Sun, the residual heat of its formation, still slowly escaping billions of years later, still warming the planet from within, even as the Sun provides warmth from without. That internal heat matters more than it might initially seem. On Earth, the energy that drives weather comes primarily from the Sun. Sunlight warms the surface warms the air, and the movement of air driven by those temperature differences is what we experience as weather. On Jupiter, the Sun's contribution to atmospheric energy is much weaker. Jupiter is more than 5 times farther from the Sun than Earth is, and sunlight arriving there is far more dilute. But Jupiter's internal heat more than compensates. The energy rising from the deep interior of the planet drives the atmospheric circulation just as strongly as any solar input, which is part of why Jupiter's atmosphere is so extraordinarily active despite its great distance from the Sun. Jupiter rotates faster than any other planet. One Jovian day, one full rotation, takes approximately 10 Earth hours. For a body so large, this rapid rotation has significant effects on its atmosphere. The atmosphere is organized into alternating bands, running parallel to the equator dark belts and bright zones that flow in opposite directions, driven by the combination of the planet's internal heat and its rapid spin. These bands are not sharp-edged features on a solid surface. They are the visible tops of an atmosphere that extends downward through layers of increasing pressure and temperature, eventually transitioning into something more like a compressed liquid than a gas, without any sharp transition marking the change from one state to the other. There is no surface on Jupiter, to speak of no place where the atmosphere ends and solid ground begins. The gas simply becomes denser and hotter as you descend, until it is compressed so tightly that it behaves like a liquid, and then denser still, until the hydrogen at the very deep interior is in a state that does not exist naturally on Earth, a metallic hydrogen, in which the electrons are no longer bound to individual atoms, but flow freely through the compressed material, the way electrons flow through a metal. The rapid rotation of Jupiter causes the planet to bulge noticeably at its equator. Because the planet is spinning so fast, the equatorial regions are flung slightly outward by the centrifugal effect of that rotation, and the poles are correspondingly flattened. The difference between Jupiter's equatorial and polar diameters is large enough to be visible in photographs. Jupiter is clearly not a perfect sphere, but an oblate one, wider across its middle than from pole to pole. This shape is another quiet reminder that everything about Jupiter operates at a scale where effects that would be negligible on a smaller body become visible and significant. Within the banded atmosphere, storm systems form and persist on timescales that have no counterpart on Earth. The most familiar example is the Great Red Spot, a persistent, stable storm system that has been observed since humans first pointed telescopes at Jupiter with enough resolution to see it, which is to say for at least 3.5 centuries. It is an anticyclonic storm, a high-pressure system larger than the Earth, spinning slowly in the southern hemisphere. It has been changing in size over the period of observation, gradually shrinking from a feature that was once 2 or 3 times the diameter of Earth down to something closer to Earth's size today. But it has persisted through those changes, maintaining its character, its color, its slow counterclockwise rotation in the southern hemisphere. Storms come and go elsewhere on Jupiter white ovals that drift in the atmospheric bands for years or decades before merging with other features. Brown barges that sit in the dark belts like elongated shadows, small convective cells that appear and disappear in the time it takes to track them. But the Great Red Spot has been a fixed, quiet, enormous feature of the planet for as long as humans have watched it. What gives it its reddish color is not entirely certain. Various chemical compounds have been proposed, including sulfur compounds and organic molecules produced by the interaction of solar ultraviolet light with the atmospheric chemistry. But the exact recipe of the color remains one of those soft, open questions that planetary science holds comfortably. The wind speeds in Jupiter's atmosphere are high, much higher than anything routinely experienced on Earth's surface. The alternating bands flow in opposite directions, at speeds that can reach several hundred kilometers per hour at the boundaries between them. The edges of the bands, where opposing flows meet, are regions of turbulence and swirling smaller vortices. But within each band, the flow is remarkably steady and organized for something operating at such scale. The stability of those bands over long periods of time, despite the enormous energy being pumped into the atmosphere from below, is a feature of the fluid dynamics of a rapidly rotating planet. The rotation organizes the atmospheric flow into these parallel streams and tends to keep them that way, dampening the kind of chaotic mixing that would otherwise blend the bands together. Jupiter's magnetic field is the strongest of any planet in the solar system, approximately 20,000 times stronger than Earth's. The field is generated by the motion of the metallic hydrogen in Jupiter's deep interior, that electrically conducting fluid churning under the influence of the planet's rapid rotation produces electrical currents, and those currents produce the enormous magnetic field that surrounds the planet. The field extends enormously far into space in every direction. If the Jovian magnetosphere were somehow visible to the naked eye from Earth, it would appear as an object in the night sky several times larger than the full moon, despite Jupiter being hundreds of millions of kilometers away. The magnetosphere on the sunward side is compressed by the pressure of the solar wind, while on the opposite side it is stretched out into a long tail that extends far through the outer solar system. The four largest moons of Jupiter orbit within or at the edge of this magnetosphere, and they experience the effects of Jupiter's magnetic environment. Continuously charged particles, trapped and accelerated by the field, bombard their surfaces, and in the case of Io, the interaction between Io's volcanic material and Jupiter's magnetic field generates an enormous electrical current flowing between the Moon and the planet, a flux tube of charged particles that releases more energy than the entire human civilization currently produces. Those four large moons, Io, Europa, Ganymede, and Callisto, discovered in the early days of telescopic astronomy, and among the first objects in the solar system known to orbit something other than the Sun, are each a world in their own right. They are not rocks orbiting a planet. They are geologically complex, individually distinct, large enough that several of them would be considered major planets if they orbited the Sun directly, rather than Jupiter. Io, the innermost, is the most geologically active world in the solar system. Tidal heating, driven by the gravitational pull of Jupiter and shaped by the resonance with the orbits of the other large moons, continuously flexes Io's interior. As Io orbits Jupiter, the gravitational pull changes slightly depending on its position in its elliptical orbit. It is pulled a little more strongly when it is closer to Jupiter and a little less strongly when farther away, and this variation repeatedly squeezes and stretches the Moon like a hand working a ball of clay. That mechanical deformation generates heat, and that heat escapes through volcanic eruptions that make Io's surface one of the most continuously reshaped landscapes in the solar system. The volcanism on Io is not quite like Earth's volcanism. Io's volcanoes produce plumes that rise hundreds of kilometers above the surface, far higher than Earth's atmosphere extends, spreading sulfur-rich material across a landscape that is being continuously buried and re-exposed. The surface color of Io is predominantly yellows and oranges and whites, the different shades corresponding to different sulfur compounds depositing at different temperatures and distances from the volcanic vents. It is a world in constant geological conversation with Jupiter's gravity, and every part of its surface carries the record of that conversation. Europa, the next moon out from Io, is covered in a layer of water ice that forms its entire visible surface. The surface of Europa is remarkably smooth and remarkably young by geological standards. Very few impact craters have accumulated there, which means the surface is being regularly renewed, old ice being replaced by fresh material from below, craters being gradually erased by whatever process is reshaping the crust. The surface is marked instead by a complex, planet-spanning network of dark lines and ridges, fractures in the ice, places where the shell has been pulled apart and refrozen, ridges pushed up by the movement of the ice shell above whatever lies beneath. What lies beneath is, based on multiple lines of evidence, a liquid water ocean. The magnetic field behavior of Europa, measured by passing spacecraft, is consistent with the presence of a conducting layer beneath the surface, and salt water would conduct in exactly the way the measurements suggest. The tidal heating that so dramatically affects Io is present in Europa as well, though at a lower intensity enough to keep a layer of water liquid beneath the ice even at Europa's cold distance from the Sunday. That ocean is thought to be in contact with a rocky sea floor, where the combination of liquid water and chemical energy from the rock might create conditions that some forms of chemistry could use. Whether anything in that dark ocean has taken advantage of those conditions is not known. It is held gently as a question rather than a conclusion, one of the most quietly compelling open questions in the study of the solar system. Ganymede is the largest moon in the solar system, larger than the planet Mercury in diameter, though not as massive because it contains a significant fraction of ice in addition to rock. It has its own internally generated magnetic field, the only moon in the solar system known to generate one, which means Ganymede has a sufficiently large and sufficiently hot metallic core, still in motion, still producing the electrical currents that sustain a field. Within Jupiter's enormous magnetosphere, Ganymede's own small magnetosphere carves out a distinct region, a bubble within a bubble, a moon's worth of magnetic territory nested inside a planet's worth of magnetic territory. Ganymede's surface is divided between two very different types of terrain: ancient, heavily cratered, dark regions that have been geologically quiet for an enormous span of time, and younger, lighter-colored grooved terrain that was reshaped by internal geological activity long after the original surface formed. The grooved terrain records a period when Ganymede's interior was warmer and more active, when the ice shell was being stretched and fractured and refrozen into new configurations. That activity has long since quieted, and Ganymede today is a cold, still, ancient world, carrying the record of a more dynamic past. Callisto, the outermost of the four large moons, orbits at a distance from Jupiter that places it just beyond the most intense part of the radiation environment, and its surface shows a very different history from its neighbors. Callisto is the most heavily cratered body in the solar system. Its surface is so saturated with impact craters that any new, large impact can only overlap an older one, because there is no unscrated ground left. The craters on Callisto are not sharp and fresh-looking. They are ancient and softened, their rims worn down by the slow creep of ice over billions of years, their interiors filled and flattened. There are no mountains on Callisto, not in any meaningful sense. There are crater rims and central peaks within craters, but no tectonic activity has ever pushed material upward from below, and so the surface has only ever been shaped by things falling onto it from above. Callisto has been geologically quiet for essentially its entire history. It never differentiated the way the other moons did, never heated enough internally to separate its rock from its ice into distinct layers, and so it remains a roughly homogeneous mixture of ice and rock, as it has been since the beginning. Together, these four moons form a system within a system, a miniature solar system in its own right, where four deeply different worlds orbit a single massive body, each shaped by its distance from Jupiter, each carrying a different story of heat and cold and geological time. Io burns. Europa hides an ocean beneath its ice. Ganymede carries its own magnetic field and its old grooved terrain. Callisto holds the ancient record of 4 billion years of impacts without alteration. Jupiter has many other moons, dozens of smaller, irregular ones, in distant, inclined orbits, captured long ago and now circling in loose, elongated paths, far from the four large ones. But the large moons are the ones with histories, with internal lives, with enough size and complexity to qualify as worlds rather than simply objects. They orbit their enormous planet in a slow, continuous procession, each in its own rhythm, each contributing in its own quiet way to the character of the largest system within the solar system. Saturn is one of the most consistently admired sights in the solar system, especially when seen through even a modest telescope for the first time. There is a particular quietness to that moment of discovery, when the planet stops being just a point of light and becomes something structured, layered, and unmistakably real. The rings appear first, almost immediately recognizable even at low magnification, as a thin, elegant extension of the planet's body. They form a broad, flattened structure encircling Saturn at an angle, as if the planet is gently tilted within a vast, invisible frame. That angle is not fixed from our perspective. Over Saturn's long journey around the Sun, which takes nearly 30 Earth years, the orientation of the rings slowly changes, so that what we see from Earth is never quite the same twice in a human lifetime. At certain points in that long cycle, the rings are opened toward Earth in a wide, graceful display. In those moments, they appear at their fullest extent, a bright and structured halo of ice and shadow wrapped around the pale golden sphere of the planet. At other times, they turn edge-on, aligning so precisely with our line of sight that they nearly vanish. When this happens, Saturn appears almost stripped of its defining feature, reduced to a calm, distant sphere, with only a thin line suggesting the immense structure that still exists, but is temporarily hidden. This slow alternation between presence and near disappearance gives the rings a quiet, rhythmic quality, as if they are breathing very slowly over decades. The true scale of Saturn's rings is difficult to grasp at first impression. They stretch outward for hundreds of thousands of kilometers, forming a system so wide that it would easily span the distance between Earth and the Moon many times over. Yet despite this vast horizontal extent, the rings are astonishingly thin. In most regions, their vertical thickness measures only tens to a few hundreds of meters. This creates a structure with an extreme aspect ratio, so thin in proportion to its width that, on a scaled model, it would appear closer to a sheet of paper than a three-dimensional object. That thinness is not a flaw in their structure. It is a natural result of orbital mechanics, where every particle finds its own stable path within a shared plane. The composition of the rings is dominated by water ice. Each particle, whether it is a microscopic grain or a fragment several meters across, is in independent orbit around Saturn. They do not move as a solid sheet, but as a vast collection of individual bodies, each following its own trajectory, governed by gravity. The inner ring particles orbit more quickly because they are closer to Saturn's gravitational pull, while the outer particles move more slowly. This difference in orbital speed creates a continuous, subtle shearing motion throughout the entire system. Occasionally, particles collide, gently exchanging energy and altering their paths. Over time, this constant interaction helps maintain the structure of the rings, preventing them from dispersing entirely into space or collapsing inward. Despite their delicate appearance, the rings are not static. They are constantly in motion, a quiet system of motion within motion. Each particle is part of a larger pattern that remains stable only because of this ongoing dynamism. The balance between gravity, orbital speed, and repeated low-energy collisions produces a structure that persists over immense timescales. It is not held together by rigidity, but by continuous motion that never fully settles. Within the ring system, there are distinct divisions and gaps where the density of material changes noticeably. Some of these gaps are narrow and sharply defined, while others are broader and more diffuse. One of the most prominent of these features is the Cassini division, a wide, darker band separating two of the brightest ring regions. From a distance, it appears as a clear separation, a gentle but unmistakable break in the continuity of the rings. Yet even this gap is not completely empty. It contains sparse particles, but far fewer than the surrounding regions, giving it the appearance of a quiet lane between denser streams of material. The reason for this gap lies in orbital resonance, a subtle gravitational relationship between ring particles and Saturn's moons. In the case of the Cassini division, the nearby moon Mimas plays a central role. Particles that would naturally orbit in that region find themselves repeatedly influenced by Mimas's gravity at the same point in their orbit. Over time, these repeated gravitational nudges build up, gradually altering their paths. Many of those particles are eventually pushed out of the region entirely, leaving behind a clearer space. This process does not require sudden force. Instead, it unfolds slowly through repetition, a kind of gravitational timing that gently clears certain regions while allowing others to remain filled. Above Saturn's equator, the planet's atmosphere extends upward into a vast and layered system of clouds and winds. At its north pole, a particularly unusual structure has been observed for a long time, a persistent hexagonal pattern embedded within the cloud layers. This formation is not a rigid object, but a stable atmospheric wave, shaped by the movement of fast jet streams circling the pole. The result is a six-sided geometric pattern spanning a region larger than Earth itself. It rotates slowly, with the deeper atmospheric layers beneath it, maintaining its shape over long periods without breaking apart or fading. The existence of this hexagon is not the result of design or intention, but of fluid dynamics operating under specific conditions. When fluids rotate at certain speeds and interact with stable pressure systems, wave patterns can form that settle into polygonal shapes. In Saturn's case, the balance of rotational speed, atmospheric depth, and temperature gradients produces a six-sided configuration. Similar patterns have been recreated in controlled laboratory conditions using rotating liquid systems, where simple circular motion naturally evolves into stable polygonal waves. The hexagon on Saturn is one of the most elegant examples of large-scale atmospheric motion organizing itself into geometric structure. Among Saturn's many moons, Titan stands out as one of the most complex and quietly remarkable. It is the largest of Saturn's moons, and one of the few in the entire solar system with a dense atmosphere. This atmosphere is thick and hazy, composed primarily of nitrogen, with methane playing a secondary but important role. The surface of Titan exists beneath this dense atmospheric layer, hidden from direct optical view, but revealed through radar and infrared observations that can penetrate the haze. On Titan, methane behaves in a way that mirrors the role of water on Earth. It evaporates from the surface, rises into the atmosphere, forms clouds, and returns as precipitation. This creates a full cycle of weather, but one based on hydrocarbons rather than water. Rain falls from methane clouds, flows across the surface, and collects into channels and basins. Over time, these flows shape a landscape that includes river-like systems, broad dune fields, and large lakes and seas, concentrated primarily near the polar regions. The surface temperature of Titan is extremely low, cold enough that water ice behaves like solid rock. At such temperatures, methane exists as a liquid, allowing it to fill the role that water plays in shaping Earth's surface features. The result is a world that feels familiar in structure, but entirely different in substance. It has coasts, channels, and liquid bodies, but their chemistry belongs to a much colder regime. The landscape changes slowly, shaped by winds and seasonal shifts that unfold over long periods. Another of Saturn's moons, Enceladus, is much smaller but equally intriguing. Despite its modest size, it displays active geological processes that make it one of the most dynamic icy worlds known. Near its southern polar region, long fractures cut across the surface. These features, often referred to informally as tiger stripes, serve as sources of continuous activity. From these fractures, jets of water vapor and ice particles are ejected into space, forming visible plumes that extend far above the Moon's surface. These plumes are powered by internal heating generated through tidal interactions with Saturn. As Enceladus orbits, gravitational forces flex its interior slightly, producing heat through friction and deformation. Beneath its icy exterior lies a subsurface ocean of liquid water, maintained in a liquid state by this internal warmth. The material expelled from the plumes contains water, carbon dioxide, methane, and organic compounds, suggesting a chemically active environment beneath the surface. Some of this ejected material contributes to Saturn's outer rings, linking the Moon and planet through a continuous exchange of matter. Enceladus demonstrates that even small, distant worlds can maintain internal activity over long periods. Its ocean remains hidden beneath ice, yet its presence is revealed through constant, gentle release into space. This process creates a connection between interior and exterior environments, allowing material from deep beneath the surface to slowly drift outward. Mimas, by contrast, appears far more static. It is a small, spherical moon, marked by a single enormous impact crater that dominates its surface. This crater gives Mimas a distinctive appearance, as if a single event nearly reshaped its entire structure. The impact that created it was so large relative to the Moon's size that it must have come close to disrupting its integrity completely. Despite its quiet and seemingly inactive nature, Mimas plays an important role in shaping Saturn's ring system. Its orbit lies close to the inner regions of the rings, and its gravitational influence contributes to maintaining gaps and structures within them, including parts of the Cassini division. Even without visible activity, its presence is woven into the dynamics of the ring system. Taken as a whole, Saturn presents a kind of slow-moving harmony. Its atmosphere, rings, and moons exist in a carefully balanced arrangement shaped by gravity, motion, and time. The planet rotates steadily, and its long orbit around the Sun unfolds over nearly 3 decades. During this journey, the appearance of its rings gradually changes from wide and open to thin and nearly invisible, then back again, in a cycle that unfolds so slowly it feels almost still from a human perspective. To observe Saturn over years is to witness a quiet transformation that does not announce itself loudly. The rings widen, narrow, and widen again, not abruptly, but with patience that matches the scale of the solar system itself. It is a reminder that even the most striking structures in space are not fixed or permanent in appearance, but part of long, gentle cycles that continue regardless of whether they are being watched. Beyond Saturn, the solar system becomes noticeably quieter in both light and warmth, as though the entire environment has gradually stepped further away from a central fire. The Sun is still present, still dominant in a gravitational sense, but its ability to illuminate and energize diminishes steadily with distance. At the orbit of Uranus, sunlight is roughly 450 times weaker than what reaches Earth. By the time it reaches Neptune, it is closer to 900 times weaker. These numbers do not translate into darkness, but into a different kind of daylight entirely, one that feels muted, softened, and distant, as if the Sun has become less of a nearby source and more of a very bright star embedded in a wide field of night. In these outer regions, light behaves differently, not because it changes in nature, but because so much of its intensity has been dispersed over the vast space it has traveled. The warmer, more energetic parts of sunlight feel less present, leaving a cooler impression overall. Surfaces illuminated in this distant light tend to appear subdued, with colors that lean toward pale blues, grays, and soft greens. The effect is not dramatic, but subtle, a slow reduction in contrast that makes even motion feel gentler. It is a region where illumination still exists, but where it no longer dominates perception in the way it does closer to the inner planets. Uranus, the seventh planet, is one of the most unusual worlds in the solar system, not because of dramatic surface features or visible storms, but because of its orientation in space. Most planets rotate with axes that are roughly upright relative to their orbital plane, tilted only slightly. Earth, for example, leans by about 23 degrees, which produces familiar seasonal cycles. Uranus, however, is tilted by approximately 98 degrees. In practical terms, this means the planet does not spin like a top, but rather rolls along its orbit, with its axis pointing almost sideways relative to the Sunday. This extreme tilt creates a seasonal pattern unlike anything seen elsewhere in the solar system. For roughly a quarter of its long orbital period, one hemisphere of Uranus faces the sun continuously, bathing in uninterrupted daylight. During that time, the opposite hemisphere remains in complete darkness. Then, as the planet continues its slow journey around the sun, the situation gradually reverses, and the other pole takes its turn in continuous sunlight, while the first falls into prolonged night. Each of these seasons lasts on the order of 2 decades in Earth time, producing a rhythm so slow that it unfolds almost imperceptibly on human timescales. The atmospheric behavior of Uranus under these conditions is still not fully understood. Because spacecraft have only observed the planet during a limited range of seasonal positions, the full range of its atmospheric dynamics remains partially hidden. What is known is that Uranus has a calm, relatively featureless appearance compared to other giant planets. Its atmosphere appears as a smooth, pale disk with a soft blue-green tint. This color comes primarily from methane gas in the upper atmosphere, which absorbs red wavelengths of sunlight while allowing blue and green wavelengths to scatter back into space. Beneath this outer atmospheric layer, Uranus is not a simple gas giant. Instead, it is classified as an ice giant because of the composition of its deeper layers. Below the hydrogen and helium envelope lie regions rich in water, ammonia, and methane in forms that behave in complex ways under extreme pressure. These materials are not ice in the everyday sense, but high-pressure fluids or partially solid mixtures that exist under conditions far beyond those found on Earth. The interior may consist of a dense, slushy, or superionic state of matter, where molecules behave neither as fully solid nor fully liquid, but as something in between, shaped by intense pressure and heat. Although faint, Uranus does possess a ring system. These rings are far less prominent than those of Saturn and cannot be easily seen without specialized observational techniques. Their discovery came not from direct imaging, but from careful observation of a distant star as Uranus passed in front of it. The starlight dimmed briefly before and after the planet itself crossed the star's position, revealing the presence of narrow rings surrounding the planet. These rings are composed of dark, low reflectivity material, making them difficult to detect and visually subtle compared to the bright ice of Saturn's rings. They form a thin, structured system that is still governed by the same orbital mechanics that shape all ring systems in the solar system. The moons of Uranus add another layer of quiet complexity. Unlike most planetary moons, which are named after figures from classical mythology, the moons of Uranus are named after characters from the literary works of Shakespeare and Alexander Pope. This gives the Uranian system a distinct cultural imprint within astronomical naming conventions, even though the worlds themselves are distant and cold. Among these moons, Miranda stands out as particularly unusual. Miranda is relatively small, yet its surface is extraordinarily complex. When it was first imaged at close range, its terrain appeared fragmented and chaotic, as if multiple geological histories had been stitched together. Large cliffs, some reaching heights of approximately 20 kilometers, cut across its surface. These cliffs are among the tallest known in the solar system, and their presence on such a small body is striking. Alongside these features are regions that appear smoother and younger, suggesting resurfacing events that erased earlier geological structures. The origin of Miranda's unusual terrain is still not fully understood. One possibility is that the Moon was disrupted by past gravitational interactions and later reassembled, leaving behind a patchwork of different surface regions. Another is that internal processes within the Moon's icy structure caused localized melting and refreezing, reshaping the surface over time. What is clear is that Miranda preserves a record of significant past activity, frozen into a still and distant world that has not been revisited in detail since its initial close observation. Its surface remains one of the more visually complex landscapes in the outer solar system. Farther outward lies Neptune, the eighth and outermost planet in the solar system. Neptune completes one orbit around the Sun in approximately 165 Earth years, meaning that since its discovery, it has only recently completed a single, full journey around its orbital path. Despite receiving very little sunlight, Neptune is not a quiet or inactive world. In fact, its atmosphere is one of the most dynamic in the solar system. The winds on Neptune are the fastest recorded on any planet, reaching speeds of over 2,000 kilometers per hour in some regions. These winds drive large atmospheric systems that can form and evolve over relatively short periods. Storm structures appear and dissipate over years rather than centuries, giving Neptune a sense of ongoing atmospheric motion despite its great distance from the Sunday. The planet's deep blue color is more intense than that of Uranus, partly due to differences in atmospheric composition and partly due to the way internal processes influence cloud formation and scattering of light. Unlike Uranus, Neptune emits more energy than it receives from the Sunday. This internal heat source plays a significant role in driving its atmospheric activity. The origin of this internal heat is still not fully resolved, but it may be related to residual heat from formation or slow gravitational contraction within the planet's interior. Whatever its source, this heat rises through the planet's layers and contributes to the strong vertical mixing that fuels its dynamic weather systems. In this sense, Neptune is not simply a cold, distant planet receiving faint sunlight, but a world generating its own internal energy and expressing it through motion in its atmosphere. Neptune is also accompanied by a system of moons, the largest of which is Triton. Triton is unusual among major moons because of its orbital direction. While most large moons orbit in the same direction as their planet's rotation, Triton moves in the opposite direction. This retrograde motion strongly suggests that it did not form alongside Neptune, but was instead captured by Neptune's gravity early in the solar system's history. It is likely that Triton was once an independent object, possibly originating in a distant region before being drawn into Neptune's gravitational influence. Triton itself is a large spherical moon with a surface that appears relatively young compared to many other outer solar system bodies. It has a thin atmosphere composed mostly of nitrogen, and its surface shows signs of active geological processes. Near its south pole, dark streaks and plumes indicate the presence of cryovolcanic activity. These eruptions are driven not by molten rock, but by sublimating gases beneath the surface. Sunlight, though extremely weak at this distance, is still sufficient to warm darker regions of Triton's surface slightly. This subtle heating allows nitrogen gas, trapped beneath translucent layers of ice, to accumulate pressure until it is released in bursts, forming visible surface streaks that extend downwind. Over long timescales, Triton is also slowly spiraling inward toward Neptune due to tidal interactions. This gradual inward motion is extremely slow on human timescales, but significant over geological periods. In the distant future, it is expected that Triton will approach Neptune closely enough that tidal forces could eventually disrupt it, potentially breaking it apart into a ring system. For now, however, it remains a stable, distant companion, quietly orbiting its planet, while slowly evolving under the combined influence of gravity, sunlight, and internal structure. Together, Uranus and Neptune represent the outermost large worlds of the solar system, where sunlight fades into a faint presence and internal processes play an increasingly important role in shaping planetary behavior. These are not inactive or frozen places, but worlds where motion continues in subtle and often unexpected ways, far removed from the warmth of the inner solar system. Beyond Neptune, the solar system does not end in any abrupt or clearly defined way. Instead, it begins to change character, as though the familiar architecture of planets gradually dissolves into something more diffuse and widely spaced. The dominant structure in this outer region is called the Kuiper Belt, a vast disk-like zone populated by small, icy bodies that extend from just beyond Neptune's orbit out to roughly 50 times the Earth-Sun distance. It is not a dense region in the way planetary systems are often imagined in diagrams. Rather, it is spread thinly across an enormous volume of space, with vast distances separating individual objects, and even more space between groups of them. The bodies that inhabit the Kuiper Belt are primarily composed of frozen materials that would behave very differently under Earth-like conditions. Water ice is common, along with methane ice and ammonia ice, mixed with varying proportions of rocky material. These objects are not fragments of a destroyed planet, but rather remnants of the early outer solar system material that formed alongside the planets but never coalesced into a larger world. In the early stages of planetary formation, there was enough material in this region to potentially build another planet. But the gravitational influence of Neptune, combined with the gradual thinning of available material, disrupted that process. Instead of forming a single large body, the material remained dispersed, locked into countless smaller orbits that have persisted for billions of years. Estimates suggest that the Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers across, and many millions more that are smaller. Despite this, the region remains mostly empty space. A spacecraft traveling through it would likely pass vast distances without encountering anything at all. The density of objects is so low that collisions are rare on human timescales, and most bodies follow stable, predictable paths around the Sunday. It is a region defined not by activity, but by persistence. A slow, ancient structure holding its shape through the quiet balance of gravity and time. Among all these distant objects, Pluto is the most widely recognized. For much of modern history, it was classified as the 9th planet of the solar system. However, as more objects of similar size were discovered in the same region, it became clear that Pluto was not unique in the way once thought. This led to the introduction of a new classification, dwarf planet. This category describes objects that are large enough for their own gravity to shape them into roughly spherical forms, but not massive enough to clear their orbital neighborhoods of other debris. Pluto fits comfortably within this definition. Pluto has a diameter of approximately 2,377 kilometers, making it smaller than Earth's moon, yet still one of the largest known bodies in the Kuiper Belt. It is not an isolated world, but part of a broader population of similar objects, each occupying its own distant orbit around the Sunday. Despite its reduced planetary status, Pluto remains one of the most complex and visually diverse bodies in the outer solar system. Its surface reveals a surprising range of terrains. One of the most striking regions is a large, pale, heart-shaped plain informally known as Tombor Regio. This area is composed primarily of nitrogen ice, and unlike the static frozen landscapes one might expect at such distances, it is not entirely still. Over long periods, the nitrogen ice within this region appears to undergo slow convective motion. Warmer material beneath the surface rises gently, spreads outward, cools, and then sinks again, creating a continuous cycle of slow movement. This process gradually refreshes the surface, erasing impact craters and maintaining a relatively smooth appearance over time. Surrounding this smooth plain are rugged mountain ranges composed of water ice. At Pluto's extremely low temperatures, water ice behaves more like rock than ice as we experience it on Earth. It becomes rigid and strong, capable of forming steep peaks and deep valleys. These mountains rise several kilometers above the surrounding plains, creating a contrast between smooth, flowing ice regions and sharply defined rocky-like formations. The overall landscape is not chaotic, but layered and structured, shaped by slow internal and external processes operating over immense timescales. Above this surface lies a thin atmosphere composed primarily of nitrogen, with traces of methane and other gases. This atmosphere is extremely faint compared to those of the inner planets, yet it is still sufficient to create subtle changes in surface conditions. At times, it expands slightly when Pluto moves closer to the Sun in its elongated orbit, and then gradually freezes back onto the surface as it moves farther away. This creates a kind of seasonal exchange between surface and atmosphere, even in the extreme cold of the outer solar system. Pluto is accompanied by a large moon named Charon, which is unusually large relative to its parent body. In fact, Charon is so large compared to Pluto that the two bodies are often described as a binary system. Rather than one orbiting the other in a simple planet-moon relationship, both Pluto and Charon orbit a shared center of mass, located in the space between them. This makes their relationship more balanced than most planetary systems. The two bodies are also tidally locked to one another, meaning that each always shows the same face to the other. Pluto always presents the same hemisphere toward Charon, and Charon does the same in return. This creates a situation where, from the surface of Pluto, Charon appears fixed in the sky. It does not rise or set, but remains in a constant position, a large, pale presence, hanging motionless above the surface. On the opposite side of Pluto, Charon is never visible at all. This mutual locking creates a stable, unchanging visual relationship between the two worlds. Farther out, in the Kuiper belt, lies Eris, one of the most massive known dwarf planets in the solar system. Eris is slightly more massive than Pluto, though marginally smaller in size, indicating a higher density and a greater proportion of rocky material. It follows an extremely elongated orbit that takes approximately 560 Earth years to complete. At its farthest point, Eris travels nearly 100 times the Earth-Sun distance from the Sun, while at its closest, it moves back into the inner regions of the Kuiper belt. Eris has a single known moon, Dysnomia, which orbits it at a relatively stable distance. The surface of Eris is highly reflective, suggesting that it is covered in fresh deposits of methane ice. These ices may have formed when Eris was closer to the Sun during parts of its long orbital cycle, allowing a thin atmosphere to develop and then later freeze back onto the surface as the object moved farther away. This cycle of temporary atmosphere and refreezing contributes to its bright appearance, even at such extreme distances. Another unusual object in the Kuiper belt is Haumea, a dwarf planet distinguished by its rapid rotation. Haumea completes a full rotation in roughly 4 Earth hours, which is extraordinarily fast for a body of its size. This rapid spin has caused it to stretch into an elongated, ellipsoidal shape, resembling a flattened oval or egg-like form rather than a perfect sphere. The centrifugal forces generated by this rotation have reshaped the object over time, giving it a distinctly non-spherical geometry. Haumea is also unique in that it possesses a ring system, along with 2 small moons. These features are believed to be the result of a past collision that disrupted a larger ancestral body, ejecting material into orbit while leaving the remnants spinning at its current high rate. The system that exists today is therefore a kind of reconstructed structure, shaped by both impact and rotation. Makemake is another major Kuiper belt object, slightly smaller than Pluto and Eris, but still large enough to qualify as a dwarf planet. Its surface is reddish in color, likely due to complex organic molecules processed by long-term exposure to solar radiation. It is covered in a mixture of methane and nitrogen ice, similar in composition to other distant objects, but with its own distinct surface characteristics. Makemake also has a small moon discovered relatively recently, which orbits it quietly in the distant cold. Far beyond the main Kuiper belt lies an even more distant and isolated object known as Sedna. Sedna follows one of the most extreme orbits known in the solar system. At its closest approach to the Sun, it still remains far beyond the main planetary region, never coming closer than about 76 times the Earth-Sun distance. At its farthest point, it travels out to nearly 900 times that distance, entering a realm where the Sun is barely more than a bright point of light in an otherwise dark sky. Sedna's orbital period is estimated to be around 11,500 Earth years, meaning that it takes more than 100 centuries to complete a single journey around the Sunday. At its farthest distance, it moves so slowly that its motion becomes almost imperceptible over human timescales. This extreme orbit cannot be easily explained by the gravitational influence of the known planets alone. It suggests that some combination of distant past interactions, passing stars, or the subtle gravitational pull of the galaxy itself may have shaped its trajectory into such an elongated path. In regions like Sedna's orbit and beyond, the solar system transitions into a realm of extreme slowness. Orbital periods stretch from centuries to thousands of years, and the movement of objects becomes so gradual that change itself feels almost suspended. Sunlight at these distances is extremely faint, reduced to a tiny fraction of its intensity in the inner solar system. Surfaces are correspondingly cold, often only a few tens of degrees above absolute zero, where molecular motion itself nearly ceases. Distances between objects grow so vast that even spacecraft traveling at high speeds would require decades to traverse relatively small portions of space. In this region, the familiar sense of a structured planetary system gives way to something more diffuse and widely spaced. It is not empty, but it is profoundly sparse, filled with objects that move so slowly and so far apart that they seem almost unrelated to one another. This outer region carries a distinct quality of stillness. It is not silence in the literal sense, but a reduction in activity so complete that change becomes rare and subtle. There are no sudden events, no rapid transformations, and no strong environmental forces reshaping landscapes on short timescales. Instead, there is a continuous, almost imperceptible drift, a slow movement of bodies through space that persists without interruption. In this sense, the Kuiper belt and the regions beyond it represent a kind of extended boundary of the solar system, where the structure of planetary motion gradually dissolves into long, slow cycles. It is a place where the sun's influence remains present but greatly diminished, and where the passage of time becomes the dominant feature of the environment. Beyond the Kuiper belt, beyond the scattered disk, beyond Sedna and the most distant objects we have catalogued, there is a region that has never been directly observed, but whose existence is inferred from the behavior of comets that fall into the inner solar system from above and below the plane, from directions that could only mean they originated in a spherical shell surrounding the entire system. This is the Oort cloud. It is thought to be a roughly spherical reservoir of icy bodies, extending from perhaps 2,000 to perhaps 100,000 times the Earth-Sun distance. The outer edge of the Oort cloud is where the sun's gravitational pull finally becomes comparable to the gravitational influences of other nearby stars and the background structure of the galaxy. The Oort cloud contains perhaps hundreds of billions of small icy objects, the frozen remnants of the early solar system, flung to these enormous distances during the period when the giant planets were migrating and disrupting each other's orbits. These objects drift at such enormous distances that their orbital periods are measured in millions of years. They are barely attached to the sun by the faintest thread of gravity. A passing star, not close, not threatening, just passing at a distance of perhaps a light year or more over a timescale of millions of years, can perturb these distant objects, nudging some of them onto paths that take them inward, falling slowly toward the sun on enormously long, arcing trajectories. When one of these objects falls inward, it may take millions of years to travel from the Oort cloud to the inner solar system. As it approaches the sun, the increasing warmth causes its ices to sublimate, to transform directly from solid to gas, releasing dust and gas that form the distinctive bright envelope and tail of a comet. Long-period comets, those with orbital periods exceeding 200 years, are thought to originate in the Oort cloud, while shorter-period comets come from the Kuiper belt. Some comets fall into the inner solar system only once, making a single close approach and then returning to the outer darkness, or sometimes being disrupted by the sun's gravity and never returning as intact objects at all. The Oort cloud is one of the places where the solar system transitions from being dominated by the sun to being influenced by the larger galaxy. The sun's gravity is still what holds the Oort cloud objects in orbit, but just barely. The tidal forces of the galaxy, the collective gravitational influence of the mass distribution of the Milky Way, are strong enough at Oort cloud distances to influence the orbits of those distant objects. Passing stars, molecular clouds, and the galactic tide all act on the Oort cloud, slowly stirring it over geological timescales and occasionally sending its constituents on long inward journeys. The outer boundary of the Oort cloud is not sharp. It is the region where the sun's gravity and the galaxy's various influences achieve an equilibrium, not a wall, not a line, but a gradual transition from one realm of influence to another. The heliosphere, the bubble of solar wind influence, ends much closer than the Oort cloud. The heliopause, where solar wind pressure balances interstellar medium pressure, is at roughly 100 to 120 times the Earth-Sun distance, well within the Kuiper belt region, and far, far inside the Oort cloud. Several spacecraft launched by Earth are now crossing or have crossed this boundary. Beyond the heliopause, the solar wind no longer dominates. The magnetic field directions change. The particle populations change. You are, in a physical sense, outside the solar system's immediate influence zone, though still in principle gravitationally bound to the sun's system. Interstellar space, the space between stars, is not empty. It contains the interstellar medium, a thin distribution of gas and dust, mostly hydrogen, along with heavier elements and small dust grains. The density is very low, far lower than the best vacuum achievable in a laboratory on Earth, but it is not nothing. It has structure, temperature, magnetic field. It flows and interacts with the edges of stellar systems. Objects crossing through interstellar space pass through this medium, and occasionally objects from interstellar space not bound to our Sun pass through the inner solar system. At least 2 such objects have been detected in recent years, recognized by their trajectories, which showed hyperbolic paths that could not be explained by any orbit around the Sunday. They passed through, briefly visible, and continued outward on their interstellar journeys, visitors from other stellar systems crossing through our neighborhood on trajectories that had been traveling for perhaps millions of years. From the outer edge of the Oort cloud, looking back, the Sun would be simply another star. Bright, the brightest star in that sky, but not dramatically so. A yellow-white point of light, similar to how other stars appear from Earth. The entire inner solar system, the Sun, all 8 planets, all of the rings and moons and asteroids would be invisible, packed into a region of sky far too small to distinguish at that distance. Everything familiar, all the worlds of the inner solar system, reduced to a single point of light among many other points of light. The neighborhood, seen from its own edge, becomes indistinguishable from all the other neighborhoods scattered across the galaxy. This is not a frightening thought. It is a clarifying one. The solar system is one arrangement of matter around one ordinary star, one of hundreds of billions of such arrangements in the galaxy. The pattern that organized itself here, the disk, the rocky inner worlds, the gas giants, the ice giants, the belt of remnants, the distant cloud, is probably not unique. Similar patterns, with variations, are forming and have formed around countless other stars. The solar system is a template of a kind, an example of one particular outcome from a very general process. And that process is continuing elsewhere, right now, in other regions of the galaxy, around other stars in other stages of their lives. The quiet neighborhood is, in the largest sense, not unusual. It is not exceptional. It is simply here, and it is familiar, and you are resting inside of it tonight. There is a quality of motion to everything in the solar system that does not require any attention to maintain. The planets are moving right now. Every moon is moving. Every asteroid in the belt is following its own slow ellipse. Every Kuiper belt object is somewhere on its centuries-long path. The comets in the Oort cloud are drifting, barely perceptibly, on their million-year circuits. None of this has paused for the night. None of it has slowed because someone is resting. The motion is as continuous as breathing, as reliable as any rhythm that simply continues without needing to be noticed. The spacecraft that have been traveling outward from Earth for decades are still moving. They are now in the space beyond the heliopause, crossing through interstellar material, carrying with them instruments that are still measuring the environment around them, and sending those measurements back across an enormous distance at the speed of light, which means the information arrives hours after it was recorded. Those signals, thin and quiet, crossing the enormous distance between a small spacecraft and its home planet, represent the farthest reach of human-made objects into the solar neighborhood. They are drifting outward at tens of thousands of kilometers per hour, and even at that speed, they will take tens of thousands of years to come close to another star. The Sun is itself moving through the galaxy. It is not stationary at the center of some fixed frame of reference. It orbits the center of the Milky Way galaxy, along with everything else in the solar system, at approximately 220 kilometers per second, completing one galactic orbit in approximately 225 to 250 million years. In the time that has passed since the solar system formed approximately 4.5 billion years, the Sun has orbited the galaxy roughly 20 times. The entire history of complex life on Earth has occurred within approximately 2 galactic orbits. One galactic year is an almost incomprehensible span of time, and the Sun has been alive for 20 of them and has approximately 20 more ahead. As the Sun moves through the galaxy, the solar system moves with it. The heliosphere pushes through the interstellar medium like a slow wave, the solar wind carving out its bubble in whatever gas and dust happens to be in the Sun's current neighborhood of the galaxy. Different regions of the galaxy have different densities of interstellar material. The Sun passes through regions of denser gas and through regions of near emptiness as it travels its galactic orbit. These differences in the external environment affect the heliosphere, changing its size and shape over long timescales. The solar system's environment is not constant even on the scale of galactic motion. But the changes are slow, and the heliosphere maintains its protective bubble across all of them. The inner solar system maintains its orbital structure with extraordinary stability over long timescales. The gravitational interactions between the planets cause slow, long-period oscillations in their orbital shapes and inclinations. The eccentricity of Earth's orbit changes slightly over hundreds of thousands of years, driven by the gravitational influence of Jupiter and other planets. These oscillations contribute to the long-period climate cycles that shape ice ages on Earth. But the planetary orbits themselves remain stable on the billions of years timescale that the solar system has so far experienced. The planets will continue to orbit. The Moon will continue to drift slowly away from Earth. The asteroid belt will continue its quiet, sparse circulation. What changes, on the very long timescale, is the Sun itself. The Sun is slowly brightening over its main sequence lifetime. It is approximately 30% brighter now than it was when the solar system formed. In the distant future, this gradual brightening will have significant effects on the habitability of the inner planets. But the pace of that change is measured in hundreds of millions of years per meaningful step, and the night you are resting through represents an infinitesimally small fraction of any of those timescales. There is something deeply restful in the idea that the solar system's structure is stable on any timescale that has relevance to anything familiar. The seasons will continue to cycle. The Moon will continue to orbit. The Sun will continue to rise each morning, delayed by its 8-minute light travel time from its actual position. Jupiter will continue its slow path around the Sun, completing an orbit every 12 years. Saturn will continue its 29-year circuit. The patterns are so slow, so dependable, so far beyond any individual variation or disruption that they represent something like a permanent backdrop to everything that happens within them. Beyond the solar system, other stars and their systems continue on their own paths through the galaxy. The nearest star system, a triple system of Sun-like stars about 4.25 light-years away, is moving on its own galactic orbit, slowly converging and then diverging from the Sun's position over millions of years. In the very distant future, tens of thousands of years from now, it will be slightly closer than it is tonight. Then it will begin to move away again. Stars pass near each other on galactic timescales, not human ones. The galaxy is full of these slow encounters, these long approaches and retreats between stellar neighborhoods, each one too gradual to observe in a single lifetime, but measurable over centuries of precise observation. The solar system is, in the end, a quiet thing. It is large, incomprehensibly large on any human scale, and it is full of motion, but the motion is measured in years and centuries and millions of years, not in moments. The 8 planets continue their orbits. The moons continue theirs. The asteroids drift. The Kuiper Belt objects trace their centuries-long paths. The Oort cloud objects hang at the very edge of the sun's gravity, waiting for the gentle nudge that might, in millions of years, send one of them falling slowly inward. And beyond all of that, the sun and everything it holds moves through the galaxy at its steady pace, orbiting a center it has been orbiting since before the Earth existed, and will continue to orbit long after any of the processes familiar to life on Earth have run their course. You are inside this system right now. You are resting on the third rocky world from a medium star, orbited by a large moon, surrounded by 7 other planets and countless smaller worlds, all moving through the galaxy in a pattern that was established billions of years ago and will continue for billions more. The motion does not need you to be awake to continue. The orbits do not require your attention. The sun will rise tomorrow in exactly the way that physics has arranged for it to rise, and it will set in exactly the way that physics has arranged for it to set, and the stars will appear after it sets in exactly the positions they have been approaching all day, and the moon will be in whatever phase the geometry of its orbit has brought it to, and all of it will be happening the way it always has. The quiet and continuous motion of a neighborhood that has never needed anything from its inhabitants, except, perhaps, this, a soft, attentive rest. The solar system will still be here in the morning. Every world in it will have moved just slightly farther along its orbit during the hours you have been drifting. The sun will have converted a small fraction more of its hydrogen into helium and light. The moon will have moved a small distance along its monthly path. Jupiter will have rotated several times. Saturn's rings will have maintained their quiet orbital structure. And on the edge of the system, Voyager will have moved another 1,000,000 kilometers or so in the direction of the stars. Let all of that motion continue without you. Let the orbits turn. Let the solar wind blow outward past every planet and moon, and into the interstellar space beyond. Let the comets drift in the Oort cloud, patient and frozen and ancient. Let the distant dwarf worlds trace their centuries-long paths through the cold outer darkness. Let the sun burn quietly at the center of it all, converting its fuel steadily, sending its light outward at the speed that light travels, crossing the 8 minutes to Earth without urgency, arriving softly, the way it always has. You can rest now. Everything is still moving, and it will keep moving, and you do not need to watch it. The solar system is very old and very patient, and it will be here when you wake. The planets will have moved, the moon will be in a slightly different phase, and the sun will be rising again on a world that has been turning through space since long before anyone was here to notice. Close your eyes and let the quiet neighborhood carry on. It knows what it is doing. It has always known. Sleep well, and good night.